All right, thank you for the introduction, for the kind introduction. By the way, being famous in Belgium means nothing. So it's like a super small country, so whatever. Thank you anyway, it makes me feel awesome. Before we start, I have a warning. So this talk is like fairly technical. It goes into a lot of depth, so it's going to be a change in pace compared to what we had before lunch. So this is ideal for the after lunch dip from the food. So you got to stay awake. It's very important. That's number one. Number two is an apology. I have a bit of a cold. It's been ongoing. If you have small kids at home, you know October, November are horrible months. They bring God knows what home from school. So if you hear cold-related sounds, my apologies for that. I'll do my best to keep it down as much as I can. All right. Enough about life. Let's talk about OAuth. Who here is familiar with OAuth? Awesome. Who here is doing OAuth like really securely? Okay. That's good. That's why I'm here. If everyone was like, yeah, we do, then I was like, okay, that was the end of my talk. Thank you very much. So today we're going to talk about OAuth. OAuth is old. I mean, it's 12 years officially spec age old. Of course, a couple of years before that being developed. So OAuth 2.0 has been around for a long time. And I think it's fair to say that when they created the protocol, people never envisioned OAuth going where it went or goes today. OAuth today is used for financial applications. OAuth is used for eHealth applications, like really security-sensitive applications are all built on top of OAuth. And if you know a bit about the history of OAuth, that's really worrying, because when they built OAuth 2, they deliberately made it easier to use and less secure than OAuth 1. And there were a whole couple of things that they said, like, yeah, we probably should do that, but you know what? We'll figure it out later. And that's what OAuth became to be and what we have to deal with today. And what I'm going to talk about today is not OAuth as defined 12 years ago or 10 years ago or whatever. I'm going to talk about some fairly recent additions to OAuth. And many of these additions have been inspired by the adoption of OAuth in financial APIs, where they had some very strict requirements and said, like, you know what you guys are doing is fine, but we want to do it a bit better. And some of these things got backported into the normal OAuth specs and so on and so on. And that means we're going to talk about jar, par, and DPoP. Awesome abbreviations. If you know what they mean, this is really helpful. If you don't, then you'll have to sit tight, and I'm going to explain it really clearly in a couple of minutes. Before we do that, I know you're all familiar with OAuth, but a few people are not, so I'm going to put down a baseline of OAuth stuff that we need to know, like absolutely the bare bones minimum of what we have to know to follow this presentation. All right? If you've been doing OAuth, this should be all familiar. If it isn't, then I highly recommend to brush up a bit on modern OAuth. So what is OAuth? What is the idea? The idea is actually that we have a client application, an OAuth client, doing something on behalf of a user. That's the generic use case that usually is done in OAuth. So our client application is at the bottom. I have a highlighter, so let's see if we can use that. Yes, here we go. It's at the bottom. It's a backend web application. So it's a backend system that's going to act on behalf of the user. And to do that, it wants to call an API on behalf of the user. And to do that, it needs an access token. That's basically the premise of OAuth. You get an access token to act on behalf of the user. And we get that access token from an authorization server or security token service. And it's going to involve some complicated interaction, which I've represented with one misleading arrow. It's like just one arrow to make this happen. In practice, it's like 8 steps or something. But that's essentially what happens in the front channel. The user will be involved. There will be some redirects. The user will have to authenticate maybe, and so on and so on. And that's a front channel interaction. That's part 1 of a normal authorization code flow. Part 2 is the back channel interaction. It's when the backend has received something. Now it has to exchange a code for tokens. It does that with back channel, secure back channel communication with the STS. That's essentially what's going on here. And then the third step is where the backend actually uses that token to access an API. So when I put this into a real-world use case, for example, I use Buffer, a social media scheduling tool, to post stuff on my accounts. So Buffer would be, in this case, a client application running their own backend systems and whatnot. And when Buffer wants to post on my LinkedIn account, that's the LinkedIn API, they need an access token from LinkedIn to make that happen. So when I click in Buffer on, like, make this happen, I'm going to be sent to LinkedIn. I have to approve that, goes back, and eventually Buffer can post on LinkedIn in my name. That's kind of the setup of OAuth. Of course, this comes in 1,000 different flavors flavors. You have clients accessing financial APIs, maybe a doctor application accessing eHealth APIs. You can think of 1,000 scenarios, and you probably have a whole bunch of those in your internal systems as well, internal company applications and whatnot. All right, that's the authorization code flow. This level is very useless. It's way too high level. I just want to highlight the front channel and the back channel. These are two very important components. This part is considered insecure. The front channel, the browser, is like whatever, especially if you're a backend web application, whatever happens in the browser is untrusted. And then the back channel, server-to-server communication today is considered to be a secure communication channel and whatnot. All right, so let me dive into a little bit more detail, because that's what we need in this presentation. I want to highlight the process of getting to that token, and it starts with the user and some intent, like the user saying, I want you to connect to my LinkedIn account or whatever I want to log in, often used together with OIDC and OAuth and so on. When that happens, the client starts a flow with an initialization. The client initializes the flow, starts the flow with an authorization request. And if you've been doing OAuth, it's a request with all the parameters in there. So it's basically a redirect. So this is a request to the browser, a response saying like, hey, you should go to the security token service. So the browser follows that, and we end up there, where the security token service now knows like, it's buffer asking to access LinkedIn. Yeah, okay, we'll see who is the user. If the STS here doesn't know who the user is, there will be an authentication step. So I'll authenticate with my username and my password. For the record, that is, I don't have a dog, so that's not the name of my dog, and that's not my real password. Just trust me on that. It's not my real password. I'm going to leave it in the middle here. Whatever. Let's continue. When everything checks out here, we actually send an authorization code back to the backend, and we do that through the front channel. That's the setup communication channel. So again, a redirect to the callback endpoint. The browser will follow that, and that results in call 7 here, where we send the authorization code to a callback on the backend. It's a query parameter, so it's very obvious. We extract that authorization code, which is meaningless to the backend because it has to exchange that code for tokens. So now it goes back to the STS in step 8, exchanges the code from step 7 for the access token and maybe a refresh token and identity, whatever. That's not relevant for today. And with that access token from step 9, we can finally access an API in step 10. Like I said, complicated. Actually, there's like a whole bunch more steps that I have omitted for brevity reasons. Pixie would take us way too far. We don't need Pixie today. But yes, you should be using Pixie in all your authorization code flows. If you have no idea what Pixie means, you have some reading to do. That's for after the conference. Good. The authorization request. What happens in step 2 and 3? That's the interesting one for at least the first part of the presentation. That's the request with all the parameters. Right? So what we're doing is we're basically sending the user, and through the browser, we're sending the user to the STS, and we're providing the configuration of the flow. Like we want to run an authorization code flow, that's line 2, response type code. As a response, we expect an authorization code. And we provide the client ID on line 4, like we're this particular client, buffer or your internal application or whatever. And when you're done, you should send the code to the callback endpoint right here, and then there's some Pixie stuff on line 6 and 7, and scopes, and so on. That's the authorization request, and that's what we'll talk about in the beginning. Good. If you are familiar with OAuth, you may have seen that I'm using like non-spec compliant terminology, which is a bit by design. I do a lot of trainings on OAuth and OIDC, and the problem is if you start talking about OAuth, you have one set of terms, and then OIDC is a different set of terms for the same concepts, which is like very confusing if you start switching all the halfway through. And that's why I use terms that mean something to us as developers, things that mean something in 95% of real-world scenarios. So we're talking about users, APIs, a security token service instead of an authorization server or an IDP, and so on and so on. So this slide is what you would use to map the stuff I talk about here in this presentation to a spec, and so on. Good. That wraps up the introduction. So who am I? I'm Philippe Ryck. I'm apparently famous in Belgium. I'll have to put that on my non-existent Wikipedia page. But what I do is I've been doing web security for a long time. I did a PhD in web security. And since my PhD, I stayed at university for a while, and then I founded my own company called Pragmatic Web Security. Well-chosen name. I help developers with security in a very pragmatic way, as in I provide them with the knowledge they need to understand it, and then the pragmaticism to help them make decisions about what would be the right approach for this particular scenario. And I do that through conference talks, courses, conference workshops like the one tomorrow, Also online courses and, of course, private trainings. So I'm quite busy with that. And I also do expert consulting on typically very complicated topics like OAuth, OIDC, helping the teams understand what it's all about, check their implementations against best practices and stuff like that. Good. What else? I'm a Google developer expert, which means I do not work for Google. It's kind of a recognition that they give out to people that contribute to the community. It's kind of an honor to be part of that program. It's not that trivial to become a Google developer expert. So it's very nice. It's a nice community, and they send some free swag every now and then. So that's also, it's kind of a win-win relationship there. All right. Finally, SecOpDev. This is a non-profit application security course, secure application development in Belgium that I run together with a couple of other people. And we bring in experts from all around the world, like Jim Manico is part of SecOpDev as well. We bring them together in Leuven to teach about application security. It's a week-long event. It's an absolutely amazing experience, very immersive. You're together with the people, you talk with people, you learn about application security, and we have some great food as well. So yeah, there's nothing bad about SecOpDev actually. So it runs in June every year, so June 2025. Mark that in your calendar, and maybe I'll see you there as well. Good. That wraps up the introduction. If you want to connect with me later, I'm very, very easy to find online, so take advantage of that. If you want to grab a PDF of the slides, this QR code is very safe, so just use that one. Just use that one to find the slides. It's a more extended deck than this one because it's also used for longer talks, and you can review that later on. If you didn't scan it, which is fine, just Google my name, you'll find my website, you'll find the slides. It's not that hard to do. Good. Back to the authorization request. Turns out that security with that authorization request is not ideal. So what we had here is we had that request in step 2 and 3, where basically a backend web application sends a kind of sensitive request through the browser. Now imagine a malicious user here, they see that request coming in, they can stop and be like, let's maybe change a parameter here and see what happens. And that kind of violates the integrity of these parameters. Now, obviously, you can't change all of them because then the thing would just blow up and the STS would be like, I have no idea what you're trying to do, go away. But if you carefully tamper with some of them, like the redirect URI, maybe the code gets sent to a different endpoint. And that might be a little bit of a problem. And that's something that came to light when we started using OAuth in like these sensitive scenarios. Like, yeah, that was probably not the best idea to have a bunch of unsigned, unprotected URL parameters as one of the steps in the flow. And that's what's going to change with the first set of requirements, the first spec we're going to talk about. Now, this is not an unknown vulnerability. This is not something new. It's not a 0-day I'm dropping here like, you can change that. It's something people have known about, and the OAuth security best practices also describe a couple of attacks against this. For example, attacks would be against the redirect URI, the attacker modifying it. Maybe if there's a wildcard in there, they can trick the STS into sending it somewhere it shouldn't go, even though it's kind of allowed. So there's already countermeasures in there to try and stop these attacks. So it's not like this is a gaping hole, but it's something that we can kind of easily fix to avoid all of this mess together. By the way, it results in real-world issues, like here's a story from earlier this year with a keycloak vulnerability allowing such an open redirect. So these are not made up. These actually exist in real-world, heavily used systems. All right, so how can we fix that? Well, we can apply jar. And jar is not the Java archive thingy, but it's, so if you search for the jar spec, you have to write jar OAuth spec, otherwise you end up in the Java world. Jar in this case is JOT secured authorization request. And the title itself kind of explains perfectly what this thing is going to do, right? We're going to take the authorization request, like all the parameters, and we're going to drop them in a JSON web token, we're going to sign it, and then send in a request. That's the TLDR version. So what does that mean in practice? It means, here's the slide from earlier with a lot more details. So it means that the client here, step 1 is the user triggering the flow. Step 2 is like generating a JSON web token. We're going to generate the token and sign it with a private key. And then we're going to drop that JSON web token in the URL here, which will go all the way here in step 6. So the green stuff is the modified aspects of a flow with jar. All right? Fairly simple, very straightforward. And all of a sudden, you get a lot more security. And that's actually really, really awesome. Good. What does it mean? It means that the URL now contains 2 parameters instead of like 18. Number 1, client ID has to be there. That's an OAuth requirement. We can't change that in any flow. So it's there whether we need it or not. In this case, it's not very useful, but whatever. It has to be there. There's no discussion about that. And the second parameter on line 3 is request. A request is a new parameter in an OAuth flow that basically tells the STS, here's a request object, like what follows is an object, and in this format it's a JSON web token. And that JSON web token, which starts with the EYJ here, and it goes all the way to the end, contains all of the flow parameters. I have some highlights here for if you're reviewing the slides later as well. Good. This JOT is signed by the private key of the client and contains all the sensitive parameters, and the security token service here has the public key of the client set up during client registration so it can verify that signature and make sure that everything is valid. So what's inside that JOT? Here's the long JSON web token on the left, encoded, very non-readable, but if you throw it in a JOT debugger on jot.io, you get a header and a payload. And the header, you can see here, the header has a type, OAuth auth plus JWT. That's a new type, specifically for an OAuth authorization request. All right? And then the body looks very familiar. In the body, we actually have all of the parameters we had before. We have the response type code, we have a client ID, we have a redirect URI, and all of these things that were in the URL before are now in the JSON web token. All right? What's new is the issuer and the audience. The issuer is the client ID. The audience is the STS, the authorization server's identity is now the audience who is supposed to consume this JSON web token. And that's essentially what we package up, what we sign, and what we send to the STS. And that's how we protect the integrity of these parameters. All right. I'm going to show you a quick demo of jar in action. Before you get like super excited, it's a very underwhelming demo, just to set expectations here. Trust me. But I'm going to show you, and so you can see that it's actually fairly easy to implement as well. So what I have is an application that is doing a normal authorization request flow. It's running against identity server in the backend, which is running on my laptop, so it's very convenient. And if we run an authorization, let me clear this, an authorization code flow, we end up at the identity server. And if you look at the flow here, you can see the parameters in the URL are right here. Like we have the client ID and the scope and the response type and all of that stuff is there. This is a normal authorization code flow. We end up here, so I now log in with my username, Philippe, and my password, fluffydog something something, or just pop, that also works. And we end up back at the callback endpoint with the code, and the code, where's the redirect? Here, we call the callback with the code. This is the authorization code that we have to exchange, and you can see on the right, that's the output of the client, the backend web application. It receives that code, it's trying to exchange that for tokens, and this is basically the set of tokens that it has received. That's the normal authorization code flow. Like I said, very underwhelming. It's going to get worse, so don't worry. So let's enable the authorization code flow with jar. So I'm going to uncomment this line and comment this line. So that's all I'm going to do. This is implemented, of course, in the demo. What we basically did is we used a library for this. There's a nice library for Node.js that actually allows you to create a request object on the client. So what we're doing here is we're creating the request object, adding the parameters that need to be in there, and then signing it. And that's what we throw into the URL. Creating the URL is a bit messy, but it kind of works. So let's do that again. If I hit this button again, we're not going to have to log in as Bob because we have a session now with the STS. So the STS knows who we are, single sign-on, and so on. So it's going to remember that. So let me show you what's going on now. So we have here the new URL. We're using jar. What do we have? We have a client ID. Well, actually, I can show you here. I have a client ID. That's the client is Node.js, very convenient. And the request is this JSON web token of what's being sent. And that's essentially how jar works in practice. These parameters are now signed. I can observe them as the attacker, but I can't tamper with them because it will result in an invalid object. So no more messing with the redirect URI, no more changing scopes, no more whatever you want to do, pixie downgrade attacks, and so on. All right? That's jar. Exciting, awesome. Takeaway, jar, JSON secured authorization requests are a big step forward. Actually, OpenID Connect had something similar. Now we have that in the OAuth world. We can enable integrity protection for the parameters in the authorization request, and it makes our OAuth flow significantly more secure. Good. Now think about this. Jar. JSON web tokens are kind of verbose. It's like a very long string. And if you put like a lot of parameters in your request, then adding all of the JOT stuff around it is going to make the request URL very, very long. So you may not like this very much. And that's a valid remark. There are some issues where the URL gets too long, where it doesn't work in certain older browsers, older devices, old mobiles, and so on and so on. So there's some concerns which are, and to be honest, it's probably not very practical. So this is great, but also not very useful. So what I've been saying for the last 20 minutes, maybe just forget about that, and let's talk about PAR. Well, not forget it, but PAR is better, so maybe if you know both of them, you can choose what to use, and my preference would be PAR. So what's PAR? PAR is pushed authorization requests. And PAR actually changes the paradigm. Instead of trying to secure the parameters, PAR is like, what if we just not have the parameters? That would be even better. All right, done. So how does PAR work? Instead of sending the parameters in the URL, PAR is going to send them to the STS first in the back channel, like, hey man, I'm going to run a flow with this configuration. STS is like, yeah, that's a good idea. Let's call this flow 17. And then you can start the flow with the browser and say like, hey, the flow is 17, nothing else. And off you go. Well, 17 is not a good random number. It's by default random number, but it's probably not a good one. So you should use like a real random value for that. But here's what PAR does. So we start the flow as normal, and the backend is like, I'm going to run an OAuth flow, but you know what? Screw those parameters. I'm going to send them to the STS first. And we're sending a PAR request, like a new type of request, submitting the flow configuration in step 2 with client authentication and all that stuff. The STS will validate that, reject it if it's invalid. Before the flow even started, it's like, no. Otherwise, it's like, yeah, that's a good idea. And we generate this unique PAR ID. And that PAR ID is sent as a response to the backend. Back channel communication, like actually server-to-server stuff, secure, and so on and so on. And now we start a flow with the PAR ID in the URL. Just a normal flow with a client ID and a PAR ID. Well, request URI, but whatever, the PAR ID. And it gets followed, the STS receives this, looks up the PAR ID, which is short-lived, temporary storage, like, oh yeah, that's the flow from 3 seconds ago, 2 seconds ago, like 2 milliseconds, whatever. And it does everything that needs to be done, authentication and so on. We get the authorization code. We exchange the code for tokens in 11, and we get the tokens in 12, and we are very happy in our backend application. That's essentially how PAR works in practice. Even better than jar. Really, really awesome. A lot of benefits here. So what does the request look like? Step 2 is a new request, a PAR request. There's a new endpoint on the STS, the PAR endpoint, and it accepts a post request with a normal payload, right? So what is here? The flow configuration. Where's my highlighter? The flow configuration from before. Response type, the scopes, the client ID, and so on, along with the client secret, because the client now authenticates during this call. Because it's a confidential client, it already has a secret. It can also be key-based authentication. I'm just using a secret as an example here. But however, authentication, however you like to do that with your clients. And that's actually a lot better, because now the STS can reject invalid flows. If you're trying to run something that makes no sense, or with an invalid redirect URI and all of that stuff, the STS is going to be upfront like, dude, no, I'm not, no. So you don't have to show an error page to the user. You can just say upfront to the server, no, and the flow ends. And if everything checks out, you get a normal response, not the error, and a normal response contains a request URI, which has this very ugly format, which is defined in the spec and registered and everything you want, but the real value is that random stuff here. That's the PAR ID. All right, so how do you use that? Well, we run step, no more 2 and 3, but 5 and 6 now. We run 5 and 6. Just like before, the client ID is always there, and then we have a request URI with that URL that we have received, or URI we have received from the STS, and that's how we run the flow. There is nothing here for the attacker to even think about tampering. You can try to guess another configuration, but you can never tamper any of the parameters. You don't even see them anymore. You don't know what's in there. Everything is hidden and handled in a secure back channel. That's what PAR really does. All right. I have a super exciting demo about PAR. So, so let's go into our application and let's enable PAR. You're kind of wishing your job would be as easy as this one, right? Like just comment stuff and off we go. I did the hard work up front, by the way. I did the work up front. Here's the code to run a PAR request. Again, the library I'm using has PAR support, which is really awesome. That's something you kind of want for On the other hand, sending a post request and handling a response, it's something as a developer you should be able to do, and otherwise I'm sure ChatGPT can do that for you. Anyway, we basically sent this push authorization request with all the parameters. The library is going to send it for us, give us the response, and then from the response, the PAR response, we can take the PAR response request URI, and off we go. Just like that, very simple, very straightforward. What happens in our demo? Let's clear this and run this again. You can see on the right the output from our client, so not the STS, but the actual client application, received the PAR response with the request URI, and then we're redirecting the browser using that PAR request URI in the object, and that's essentially all you need to know about PAR in this demo. It just works. And it's actually very useful, very beautiful. When you use PAR, this is kind of important, when you use PAR, you should configure your STS to not allow a regular authorization code flow anymore. All right? Just force the client to always use PAR, and that's the recommended security setting, and then you are highly elevated in security compared to a normal traditional OAuth authorization code flow. So PAR is really, really useful. It eliminates the need for configuration parameters in the front end. It completely eliminates the attack vector. It honestly only has benefits. It makes everything better. And it's actually so good that this is going to become the default way for running authorization code flows. So I wouldn't be surprised if in a year or 2 years, PAR is the normal standardized OAuth authorization code flow, and the other flow is considered legacy or deprecated or whatever. All right? So the people raising their hand like, yeah, we're doing secure OAuth, are you using PAR? Come on, let's be honest here. Yes or no? No, you can tell me privately, it's also fine. We'll go to the confession booth around the corner and you can say it, talk to me then. Yes?
You showed in the sample that this is supported in Identity Server.
Yes.
Which has some commercial issues at the moment, I believe. But is this supported in any of the major vendors, like Microsoft or OAuth2.0 or...
All right. So the question was like, yeah, Identity Server supports this, but they have... You call it commercial issues. I would call it they want to be paid for their work, but that's a different discussion. I strongly disagree with the characterization, by the way. But what about other vendors? OAuth2.0 has it with commercial issue. What was it? Commercial issues, as in it's their enterprise plan. So it costs probably like 5 Identity Server licenses to get it in OAuth2.0. This is being recorded. I should be careful, probably. But no. Support for this has been growing, especially because OAuth has this high security configuration now, and vendors which have been lagging behind have been forced to update. So, for example, OAuth2.0 has added a lot of these high security features recently because people were basically like, either you add them or we're going to use something else. So, yes, you'll find a lot of vendors offering them. No, I don't have an exhaustive list, and I don't believe that Microsoft has it, but I'm not sure. I would have to look. It wouldn't surprise me that they would add this, because I think PAR has been added in the .NET framework as a feature, so built in as a feature, the client side then. So it wouldn't surprise me that they would offer it on the server, but I don't have an exhaustive list. My apologies. Yeah, sure. I'm only halfway through, but let's do questions. Why not? How is the integration in Spring Boot? Let me know if you find out. Like I said, I don't have an exhaustive list, also not for client-side implementations. So this example is in Node.js because it's a quick and dirty example. It has a library that supports that. I don't know if Spring Boot supports it. The cycle there is also a bit slower to get things integrated. So to be honest, I have no good answer on that. Yeah. Yes, that's the authorization request.
That's optional, though. I can do that just during registration time and never send it over a front channel. So I can already accomplish that in standard RFC
Well, if you would do everything configuration-based, then you're limited to a single URI. I don't think that the redirect URI parameter is optional, so I think it's required, which would also mean it has to be there, even though the configuration may not support it. And the real problem comes from, you're correct to say, like, if you're doing everything spec compliant, this shouldn't be an issue anyway. But the story I showed you from Keycloak is that they do allow flexible configurations. And most vendors do allow wildcard configurations and stuff like that, and it's basically a recipe to shoot yourself in the foot because of a misconfiguration, something you missed, and stuff like that. So, as always, if you lock things down as much as you can, maybe this isn't an issue, but using PAR makes everything easier and just removes the whole attack vector altogether. So, it's like for cross-site scripting saying like, yeah, use sanitization everywhere. And it's like if you just remove the fact that HTML can get into the DOM, then the whole problem gets better in every aspect. So, all right, good. Now, no more questions because I have one more topic to cover in 13 minutes. Only sender constraint tokens, so that if you're familiar with that, that should be perfectly possible in 13 minutes. So hang on for the wild ride. No, I'll make it, no worries. Sender constraint tokens, what is this all about? Access tokens in OAuth are very often bearer tokens. And a bearer token means that the access token you use here, when calling the API, a bearer token means that the holder of the access token, like the bearer of the token, automatically has the authority to use it. Maybe they're not supposed to, but they have the authority to use it. Compared to the key to your house, if somebody has the key to your house, they can use it. Nothing is preventing them from using it. You don't have to know a secret to use it. It's just like if you find the lock where it fits, boom, and you can use it. Same with an access token. If somebody has it, it can be abused, and it has resulted in issues like a stolen access token being abused, or a compromised API receiving an access token and be like, haha, now I'm going to call another API on behalf of that user. A lot of misbehavior can result from bearer tokens. Now, bearer tokens are something that everybody knows is bad, and yet everybody uses it. It's who here is not using bearer tokens when they're doing OAuth? Right? I mean, the room speaks for itself in silence. So let's fix that. Sender constraint tokens is one of these things that they said in the beginning with OAuth, like, yeah, we probably should address this, and it kind of never happened until a couple of years ago when people said, like, you know what, we're doing this OAuth stuff, we really want sender constraint tokens. And there have been a lot of ideas and a lot of promising paths, and eventually two things emerged as potential solutions. Option one, using TLS-based certificate-bound tokens, so MTLS, mutual TLS, and option two is using DPoP application-level proof of possession mechanisms. All right, let's talk about MTLS very briefly. MTLS is basically where the client uses a TLS certificate and corresponding keys to set up a mutually authenticated session, a TLS session, which basically means that you verify the certificate of the server and the server verifies your certificate. Verification there is dependable on how you configure things. With OAuth, the server doesn't have to verify the client's MTLS certificate. It can be a self-signed cert, it doesn't matter, as long as the STS knows during client registration what the client's cert is supposed to be. All right? So we provide the STS with the configuration of the client certificate. And what happens then is the client sets up an MTLS connection using that certificate and the corresponding private key, and over that connection, they exchange the authorization code. And the security token service observes this and it's like, okay, yeah, that's your certificate, that's good, I know who you are. It also uses that certificate for client authentication, so that's easy. And it will bind the tokens to that certificate. Concretely, it adds a fingerprint of the cert into the access token, and it gives that to the client. And the client wants to call an API with that access token here, so what does it do? It sets up an MTLS connection with that same certificate, calls the API with the access token, and the API is like, hold on, we'll see about that. And it verifies that the fingerprint in this access token corresponds to the certificate used to set up this connection. And only when they match will this be a valid request. And if they don't match, it will be invalid, the connection will be closed, bye-bye, and you're done. And that's basically how you provide sender constraint tokens with MTLS, right? Very easy, very straightforward. Easy, why? Implementing this in your application takes like 1 or 2 lines of code, basically configuring your TLS library. Here's the client cert, please use it. Done. Everything else is handled in TLS libraries under the hood. Absolutely awesome. All right, so what we have here is we have the access token. That's a sender constraint token. It has a new claim, CNF, stands for confirmation. And confirmation, in this case, is with an X509 certificate thumbprint, X5T, in a SHA-256, whatever. That's the thumbprint of that certificate, embedded in the access token. So whenever an API sees a token like this, it is required to check that fingerprint and reject the access token if it doesn't match the certificate. Sounds super awesome and easy in PowerPoint, right? On PowerPoint, that's the awesome job of a consultant. Just do it like this, bye-bye, and off you go. In reality, using MTLS is kind of tricky. In reality, MTLS, if it works, it's great. If you don't control the environment, if you don't control the library under the hood, if it's in a browser or a mobile device, this is going to be a mess. And it's not always that trivial to get this working. And that's why there's a need for an application-level mechanism as well. And that is where DPoP comes in. And DPoP is significantly harder to implement because there's a lot more work to be done, but it gives you the flexibility to use it in the way you want without having to rely on TLS libraries and so on. And that's what I want to spend the rest of my time on talking. So DPoP in 8 minutes. That's a crash course on DPoP. DPoP is a spec. It has been finalized since September last year. So it's a very new edition. The idea has been around for a while, but the fine-tuning took a bit of effort. But now we have a DPoP spec, which also means once the spec is finalized, that you'll find DPoP implementations. Because many people wait until the spec is finalized to implement it because it will change anyway, and then you have to go back and change your implementation and so on. So DPoP. Let me talk to you about the concept of DPoP, not the implementation details, but the concept. How does it work? It involves a whole bunch of steps, so I'm going to walk you through it step by step, and we'll see where we end up at the end. The concept is the same, proof of possession. We want to prove to the API that we possess the secret associated with an access token, sender constraint tokens. So to do that, the client generates a new public-private key pair on the fly. It doesn't have to be re-registered, just a new key pair on the fly. And with that private key, it signs a DPoP proof. That's basically a DPoP proof showing to the STS in a second that I possess a private key because I've generated a proof and signed it with a private key. And then we ask to exchange the code for tokens, or a refresh token for tokens, same flow. And we provide a proof and a public key. So now we told the STS, like, here's our public key from the key pair, and by the way, here's a proof that we signed with a private key, which you can now verify with that public key. So we basically prove that we possess the correct artifacts, and in the DPoP proof, there's a bunch of details about what we're doing. STS will verify that, and if that's true, it will bind the token to the public key. So the access token is now bound to a public key and sent back to the client in whatever response, the authorization code response. Good. Next, we want to call the API. But we have to prove now that we possess the private key before we can do so, which means that we have to generate a new DPoP proof. Now it's a proof to call the API. We sign it again with our private key, and we call the API with the proof and the access token. API sees the access token, knows it's a DPoP token. I'll tell you in a minute how it knows that. And it's like, hold on, I'm going to check the proof first, make sure that everything is correct, that it's correctly signed, and so on. And then we can be sure that this is a legitimate client making the call, and everything happens after that. Good. That's DPoP from a high-level overview. It ensures that only the client holding the private key from step 1 can use the access token in step 8. If somebody else tries to use it, there's probably not going to be a correct proof, so it will not work. All right, and DPoP has been designed in such a way to make all of this possible, and also counter all the common attacks like replay attacks and abusing a proof from a previous request on another request. All of that stuff is covered in DPoP. It took a lot of effort from people in the community to build that spec the way it is today. All right, let's zoom in on each of these steps, or almost all of these steps. Step number 2. Step number 2 is about the proof needed to exchange the code for tokens. The proof is a JSON Web Token. It's a signed JSON Web Token. So if you dislike JSON Web Tokens, stay away from DPoP. You'll be miserable all the way through. It's entirely built on JSON Web Tokens. What we have here is we have a header. It's a DPoP JOT. We put our public key in that token, in that header, and we provide a payload here, which is the endpoint on the STS to exchange the code for tokens, the token endpoint, and we are sending a post request. So the HTML or HTTP method and URL are embedded in the proof. And that's signed by the client's private key. I have some highlights here of what it means. I'm going to skip over them in the interest of time. You can review them later. All right. This JOT is signed by the client's private key, included in step 3. along with the public key, which is part of the JOT as well. That's the request here. We send a request to the token endpoint to exchange the code for tokens, and we now add a DPoP header with our proof. That's how the STS receives this, and how the STS can verify all of the details. Good. Step 4, the STS verifies that the client possesses the private key, meaning signature verification of the signed proof with the public key, and if everything checks out, then we are happy with that. Good. We sign the tokens and bind them to the public key. Access token, confirmation claim, it's now a GKT, JSON Web Key thumbprint. If you speak JOT, you know a lot of 3-letter abbreviations. Makes for a nice bingo game for the evening. But JKT, JSON Web Key thumbprint, it's basically the fingerprint of the public key. All right. Good. So now the client has a sender-constrained access token. We want to call the API. What do we need to do? Well, actually, it's repeat the same steps. We generate a DPoP proof. DPoP proof right here. Again, the header, our public key is in there. What do we put in there? The API endpoint we're going to call, it's a GET request to this specific endpoint. We include a hash of the access token, so that this DPoP proof is linked to the access token as well. That's one of the things that changed in the spec to ensure that the token, a proof cannot be used from one request on a second request. It belongs to a specific access token on a specific endpoint with a specific timestamp and so on. All right. There's also a unique ID here that allows the API to detect replay attacks of a previous proof. All right, again, this is signed by the client's private key, and that's what we sent in step 8, along with the access token, and the API can now verify that. How do we send it? We send the access token in the authorization header. Usually it says bearer here, now it says DPoP. This is no longer a bearer token, this is a DPoP sender-constrained token. So when the API sees this, they know, like, hold on, before I use this, I have to verify the DPoP proof and all of that stuff. Where's the DPoP proof? Well, in the DPoP header. So there's the DPoP proof right there. All right, and now the API has everything it needs to verify this. This is quite a complicated process, so I'm not going to go to the details. It has to verify the signature, verify that everything matches, and only when all of these constraints are met, only when all of this checks out, then will the access token be valid. And this, like I said, it's a lot heavier than MTLS because you get no lifting from the network library, but you can do this in a flexible way. You can implement this in any language you want, on any platform you want, for any type of application you want. And it takes away bearer tokens, a significant weakness in OAuth deployments. It removes bearer tokens in favor of sender-constrained tokens. A very explicit requirement for sensitive areas such as financial APIs, healthcare APIs, and so on. So this is definitely something to consider. All right, this was probably a wild ride, a roller coaster in OAuth security. Like I said, a lot of details, perfect after lunch. Let me narrow it down into 3 takeaways. First of all, confidential OAuth clients, like OAuth clients running on a backend system, should seriously increase their security. The default OAuth flows that we've been using, they have had some upgrades, so it's time to start using them. Make PAR the default for your authorization code flows. It makes things a lot better. It removes an entire attack vector. There's only benefits to it, as long as you have library support, and even then, not having library support doesn't make it that hard to implement and release that library. And then sender-constrained tokens should be preferred over bearer tokens. That's the takeaway right here, because it makes, and again, a whole problem a lot better, a lot easier, or a lot harder to abuse, not easier to implement, harder to abuse. All right? That's essentially what I wanted to say. To wrap up, if you want more, I'm running a full OAuth course with all the dirty, nitty-gritty details in February. It's an online class, so if you want to join that, be my guest as well. You'll learn more about OAuth than you want to know, probably. And with that, I think it's time to wrap up. The slides are online as well, so you can get it there. I want to thank you for being here. I hope you enjoyed the conference and maybe the workshops tomorrow and the social event tonight. And yeah, thank you very much.